Okay, collision theory. As you can see in the learning goals, we will use collision theory along with potential energy diagrams and the Maxwell-Boltzmann distribution to explain how and why factors affect rate. Factors such as temperature, concentration, surface area, the nature of the reactant, a catalyst, etc. Okay, so this will involve being able to draw and describe potential energy diagrams and explain the significance of the Maxwell-Boltzmann distribution. So the main premise of collision theory is that reactants convert to products by successful or effective collisions between the reactant particles. So you'll see that I use those two words interchangeably. Successful here, right, and also effective. So the idea is that a successful or effective collision actually means that reactants convert to products. Products are formed. So it's possible to have an unsuccessful collision or an ineffective collision, one where reactant particles collide and then do not change or convert into products, and they're still reactant particles after the collision. So essentially they just bounce off each other. So collision theory predicts then that collisions will be successful if the reactant particles collide with, first of all, a minimum energy that's required to produce products. And that'll be different for different reactions. We call this minimum energy required to produce the products activation energy. And you'll see that we label that in the graph below in a moment. It's also important that these particles collide with the proper spatial orientation, which we'll refer to as the collision geometry. So in this example, you'll see I have A, reactant A, plus BC, and then in the middle you'll see there's an activated complex. All right, so we'll build the potential energy diagram as we go here. So the reactants, you can see I've set the potential energy of the reactants to be rather low here. And then going back to the equation here, as A strikes B, a bond begins to form, and at the same time the bond between B and C starts to be broken. So the intermediate species, the complex where A is partially bonded to B and B is partially bonded to C, we call this the activated complex or transition state. That's another name for it. The activated complex on the graph is right where I've put the star. It's the point where the potential energy is the greatest, higher than both reactants and products. Now, as long as this activated complex can form, so if the reactant particles do possess the minimum energy required to produce products, so as long as that activated complex can form and that there was proper spatial orientation or proper collision geometry, then we'll see products formed. And so the products are A, B plus C. So in the forward direction, we read this graph that reactants form the activated complex and then continue to products. Okay, now you'll notice that I'm extending the potential energy of the reactants so that I can indicate the vertical change here in Y values, the change in potential energy between the reactants and the products, and label this our enthalpy change. You'll notice that with the products finishing higher in potential energy than the reactants, that delta H is positive. So would this be then the potential energy diagram for an endo or exothermic reaction? Hopefully you thought endothermic when delta H is greater than 0. Okay, now how do we indicate the activation energy? Well, from the reactants, that baseline, we draw straight up then to the, sorry, that wasn't very straight. And that's still not very straight. Well, we're showing the difference between the potential energy of the reactants and the potential energy of the activated complex. And we can label this as E activation energy. So there's an illustration of the activation energy. Now, can you repeat this diagram, except now draw it for an exothermic reaction. So go ahead and label the potential energy of the reactants, the products, label delta H, show where the activated complex is, and the activation energy. Okay, and then check back with the video. Okay, so you'll see that all the features of this graph are the same as the endothermic, except that the potential energy of the products is lower than the potential energy of the reactants. And so there's been a release, the system has released energy to the surroundings. Delta H is negative as a result, and that corresponds to an exothermic reaction. Delta H is always labeled between the potential energy of the products and the reactants, so you'll see that. And activation energy is labeled between the baseline of the reactant's potential energy and the activated complex. Okay, when we determine rate, we think of these collisions happening. There's a percent of those collisions that will be successful based on the activation energy that the particles possess. So the percent of the collisions that will be effective or successful relates to the activation energy. Particles need to possess at least that energy. The frequency of collisions, we think of this as the number of collisions per second. And it's for it's whether those collisions are successful or not. It's just literally the number of times that the particles are colliding per second or per time unit. So let's just look at that formula in a few different examples. So let's say we have a frequency of collisions, 100 collisions per second, and we're going to say that 50% of those are effective. So following that formula then, our frequency of 100 and the percent at 50%, we'll take 50 divided by 100, they're 0.50, and 50% of the 100 collisions per second means we're going to have 50 collisions per second. So that's the rate if 50% of the collisions are effective and the frequency is 100 collisions per second. Now let's increase the frequency. So maybe 200 collisions per second, but keep the rate at 50%. Now the rate will be 200 times that 0.50. So now we've raised the rate to 100 collisions per second. So when we're stating the rate, we mean 100 successful collisions per second. So you can notice that the frequency was changed, right? And as a result, the rate changed. As we increased the frequency of the collisions, we increased rate. Okay, now what about the second factor here, the percent of effective collisions? Let's stick with that 200 collisions per second. But now let's increase the percent effective. Let's say now 75% of those collisions are effective. So now we'll be calculating 200 multiplied by 0.75. So we'll come up with 150 collisions per second. So have a look now that when the frequency was kept the same and we changed the percent effective, we increased it. Look at what happened to the rate. The rate also increased. So increasing the percent of effective collisions will definitely increase the rate. So what we do in the rest of the lesson now is examine each of the factors that affect rate, and we are looking to decide whether they affect the rate by increasing the frequency, by affecting the frequency, or by whether they affect the percent of effective collisions. In order to affect the percent of effective collisions, there needs to be some effect on the activation energy. So somehow there has to be a relationship to that. Okay, keep that in mind. So let's have a look at temperature to start. So number one here is temperature. So consider all the students in the class moving around as samples of a gas at 20 degrees Celsius. They are vibrating, rotating, and translating through the room, and of course they're going to be colliding with other gas particles. So if that sample of gas is at 20 degrees Celsius, then there's a certain kinetic energy that each particle has. Now, are they all identical? No, but that average kinetic energy corresponds to a temperature of 20 degrees Celsius. What happens if we transfer thermal energy into the room and raise the temperature? So now the temperature is 75 degrees Celsius. Well, what would you do physically, going from 20 degrees Celsius to 75 degrees Celsius? Hopefully you'd start moving faster, right? Increasing kinetic energy as we increase the temperature. So as those particles start to move faster, aren't they going to be colliding more often? Certainly they will be. You can imagine that in our room. So if the particles are going to collide more often, we've increased the frequency of the collisions. So temperature affects rate by increasing the frequency of collisions. Now, let's consider whether it affects the percent of effective collisions. And here's where we need to understand this idea of the Maxwell-Boltzmann distribution. And really it's just a pictorial representation of exactly what we would model as a group of students in the classroom. If we're a sample of gas at 20 degrees Celsius, is everyone in the room moving with the same kinetic energy, or is that 20 degrees Celsius just a measure of our average kinetic energy? Well, certainly it is a measure of our average. Some students are moving slower than others, some students are moving faster, and there's a significant number with a moderate kinetic energy. And that's exactly what this Maxwell-Boltzmann distribution shows us. So the first thing to notice is that the y-axis is labeled with the number of particles. This is not a potential energy diagram. So don't get them confused. This is not a potential energy diagram. The y-axis is the number of particles, and the x-axis is the energy. You might think of it as kinetic energy. So at this point on the graph, is this point right on the graph representing a high number of particles or a low number of particles? Hopefully you're thinking a low number because you read across to the y-axis and realize that's pretty close to the origin. How about the energy of these particles? High or low or moderate? Hopefully you're thinking low, because certainly being down here, I'll call it x1, on the energy axis here is quite close to zero. So that particle is moving very slowly. Now, if I go up to this point on the graph, I certainly have a higher number of particles. And if you track that all the way down, x2, certainly these particles have more energy than they did at x1. It's not super high, but it is greater than what they had, than the particles that were represented with an energy of x1. Up at the peak here, well, whatever this particular kinetic energy is, and it's certainly faster than the other ones we've indicated, that's the energy that's the most common energy that the particles have, which seems to be kind of moderate here. If we were to move all the way up the curve to this point here, we'd see that we're back down to a very low number of particles there, but that the kinetic energy is quite high. We're quite far on the right side of the axis. So what's important to remember with this distribution is that the area under the curve is telling you about the number of particles. So what do I mean by that? Well, how many particles are in this sample? Well, that would be the entire area under this entire curve. That represents all the particles in the sample, so the total sum. So even though on the y-axis over here you can read perhaps that one particle has this kinetic energy, and 6 particles have this kinetic energy, and 10 particles have this kinetic energy. The area under the curve, all of this, so the actual size of that area, would represent the total number of particles in the sample. All right, so there's certainly, if I were to box this out a bit, I would say x2 is, just starting to increase really in kinetic energy. So I'm going to say that this region here, right, the area of this region here, that area shows us that few particles have low low kinetic energy. And if we were to look at the range between x2 and, let's say, this range, this seems to be where the area of the curve is largest. So I'll just show this one in yellow. So the idea here is that most particles, just again, based on the size of the area that's shaded yellow, that most particles have moderate kinetic energies. And certainly as you get up into the high, so in this region down here, we're seeing that the area under the curve there would be much lower. So I'll just stick with the yellow here. But the idea here is that there are few particles with higher kinetic energies. Okay, so the basic interpretation to begin with is that the area under the curve tells us about the number of particles. So the total area under the curve of the entire blue section under the area of the curve here would be representing the total number of particles in the sample. Most of the particles have moderate energies right around here, right? And a few of them, this is a smaller area, have low kinetic energies, and fewer still have higher kinetic energies. Okay, so I'm just going to redraw this diagram without the shaded areas because I'd like to introduce the idea of activation energy onto the same diagram. Okay, so I've redrawn the XY axis and tried to mimic the blue curve that I drew in the first diagram. So now what I'm going to indicate is, let's say at this point right here on the energy axis, that is the activation energy right there. That is the minimum energy required for for the particles to possess in order to collide successfully. So notice the area under the curve. Notice the number of particles that possess that energy or greater. So on our energy axis, energy is increasing in this direction. So if this is the activation energy, then all of the particles that possess these energies have even more than what's required. But the particles with these kinetic energies, these particles do not have enough energy to collide successfully. So you can see that the green is a much larger area and the red is a smaller area, right? So what we're showing here is that there's a small number of particles that are actually able to collide successfully. There's a small number of particles that possess that minimum required energy. And how do we know there's a small number of particles? Because the area under the curve is small. Right? And there's a larger number of particles that do not have the required activation energy. Okay, so we've been asking, how does temperature affect the reaction rate? Well, imagine this blue curve here is a string. Okay, this blue curve is representing a sample of a gas at a particular temperature. We want to now draw a sample of a gas, the same gas, but at a higher temperature. Well, if you increase the temperature, the particles are moving faster, which means they have greater kinetic energy. So we need to pull the string, stretch this blue string, and imagine the blue string is not a different length. So we're literally going to pull on it, and that's going to cause this peak to lower. So perhaps I'll use yellow here. So I'm going to show what happens as we raise the temperature. So the yellow is T2. The blue was T1, and we can say here that T2 is greater than T1. So the higher temperature stretches further to the right along our x-axis, showing the increase in kinetic energy. I'll just extend that axis here. Okay, so how did increasing the temperature affect the number of particles able to collide successfully? I'm just going to extend this red line up here. Look at the area under the blue curve. We already said that there was quite a small number of particles. Right? Now let's look at the area under the yellow curve that possess the activation energy. All of this area here, isn't that a larger area? So at higher temperatures, the area under the curve is greater, right? For particles that possess this activation energy. So what we've done by doing that, or shown there, is that more particles have the potential to collide successfully, so we've actually increased the percent of effective collisions. And so in summary, temperature is shown to both increase the frequency of collisions as well as increase the percent of effective collisions. And that's why temperature is an excellent way to control the reaction rate. Okay, so we just need to go through our other factors, but temperature was definitely the longest one there. Second factor to look at is concentration. Okay, so I'm showing a reaction vessel, imagine it to be a beaker, and there's a substance. I put 8 blue dots inside each one here. So in the first beaker, I'm going to put only 3 red dots. The red and the blue dots represent the reactant particles. Those particles need to collide with the right geometry and possess at least the activation energy in order to produce successful collisions. So with only 3 red particles there, we have a certain number of collisions that will occur, and whatever percent effective are effective, we'll have that be determined, or will determine the rate. Now in the second beaker, I'm going to put more than 3 red dots. So I am essentially increasing the concentration of red here. So square brackets meaning concentration. On the left side we have a low concentration of red, and on the right we have a high concentration of red. So I have just changed the number of collisions per second. Wouldn't you agree that red and blue are going to collide more often in the beaker on the right than they are on the left? And that's essentially why concentration affects rate. It increases the frequency of the collisions. Okay, considering surface area. To illustrate the difference here, you'll notice that the blue reactant in the beaker on the left has what we consider a low surface area. And why is this a low surface area? Because the sample, maybe it's zinc metal for example, is all in one piece. Whereas if you look at the blue solid in the beaker on the right, this has a higher surface area. We've broken up, whether it's been ground into a powder or just smaller pieces. The point is more of the blue circles, the blue particles, are now available to have collisions with the other reactant red particles. So increasing surface area increases the frequency of the collisions that can occur. So we haven't changed the percentage, but again, as with concentration, we've increased the frequency of the collisions. And so both surface area and concentration affect rate for the same reason. They increase the frequency of collisions. Okay, moving on to number 4. Okay, looking at the chemical nature of the reactant. First of all, we can address this from the number of bonds. If there are fewer bonds to be broken, then we can imagine that there'll be a faster reaction rate, so just a less complex reaction. Now what about the strength of the bonds? If they're weak bonds, then we'll see lower activation energies. So how is it that a lower activation energy then links to a faster rate? Whereas if they're stronger bonds, more energy is required, higher activation energy indicates a slower rate. So I've indicated here in red activation, or EA1. I'm just realizing perhaps I'll do the green first. So I'll indicate an activation energy here with the idea that a lower activation energy, so in my diagram I'm writing that as EA1. So that would be this energy here. So think about all the particles that would possess the required activation energy, represented by the green area. Okay, now, if there are stronger bonds present, then a higher activation energy will be required. Let's call that EA2. So here's my EA2. Now look at the area under the curve that I'm marking in red. So again, the area under the curve in a Maxwell-Boltzmann distribution represents the number of particles, the total number of particles possessing at least that energy. And so the area under the red curve is definitely smaller than the area under the green curve. So can you see how the fact that the area under the green curve is larger means that there's a greater number of particles possessing the required activation energy to collide successfully. And so we see that having a greater number of particles possessing the minimum energy required to be successful, that activation energy, means that we'll have a greater percent of effective collisions. So we've gone from maybe 25% of the curve, or 20% being represented here by the red curve, to having not quite 50, but probably 35 to 40% of the particles actually possessing the required activation energy. So a lower activation energy definitely translates into a faster rate by increasing the percent of effective collisions. And conversely, the higher that activation energy is, the smaller the area under the curve, the slower the rate. Okay, and the last point about the nature of the reactant is that if you have more complex molecules and ions, then that collision geometry may be more difficult to achieve. Okay, the last factor here, catalyst. So I've drawn both diagrams now, the Maxwell-Boltzmann distribution on the left and the potential energy diagram on the right. I happen to have shown the potential energy diagram for an exothermic reaction. It could have been drawn for an endothermic. The way that we think catalysts affect rate is by providing a different energy pathway for the reactants to convert to products. So one that lowers the activation energy. That's easiest to be seen, I think, in the potential energy diagram if you're comfortable labeling the activation energy. So remember in our earlier diagrams, we labeled this height here as the activation energy. Now, what do we think a catalyst does? We think a catalyst provides a lower height hill, if you will, a lower energy pathway. So the green pathway here is catalyzed. And hopefully you can see that the activation energy for the catalyzed reaction is actually less than the activation energy that I originally drew for the blue curve that I labeled in red. So if you lower the height of the hill, it's easier to get the ball over. The students themselves trying to roll the ball over the hill don't have any more energy than they did the first time. So it's the height of the hill that has dropped. And so more of the students will be successful on that lower hill than we had for the number that were successful on the higher hill. So the catalyst provides a lower energy, a lower activation energy pathway. How can we see that on the Maxwell-Boltzmann distribution on the left? Well, the activation energy is indicated on the energy axis. So if I push it up here to the further right of the x-axis, I'm saying that the activation energy at that point shows a relatively small number of particles because of the small area under the curve. A relatively small number of particles possess the required energy to collide successfully. If we lower the activation energy or provide an alternative pathway that has a lower activation energy, you can see that the area under the curve now for green is much larger. And so by increasing the size of the area under the curve, we've shown that more particles will have the activation energy to collide successfully. And so in summary, the catalyst affects the percent of effective collisions. So if you look back through the lesson, you'll see that temperature, surface area, and concentration all affect the frequency of collisions. Temperature, the chemical nature of the reactant, and the catalyst all affect the percent of effective collisions. Okay, thanks for staying with this, and I'll take your questions and we'll discuss it further in class.